Study Unit 6, Lecture 3. This lecture carries on with single-phase, half-wave, and full-wave rectifiers. In the rectifiers I have to consider thus far, during the negative part of the input signal cycle, energy can be transferred from the load back into the supply. In half-wave rectifiers, this is rectified by making use of a freewheeling diode, which is in a shunt configuration with the load. So essentially what this diode does is that it tries to prevent the output from falling to a negative voltage, which would cause current to flow back towards the supply. Good reason why this will be done is simply because more energy can then be stored in the supply, or rather in the load. So ideally there are two conditions in this circuit over here. The first is when there is a conduction path from the supply through the thyristor and through the load. And this is given by this Kirchhoff voltage equation over here, where the voltage across the resistive and the inductive element are equal to the supply voltage. And this would be true for omega t between alpha and pi. What this means graphically is that between this delay angle alpha here and the point of the half cycle pi over here, there will be some output voltage equal to the supply voltage across the two elements in the load. The second condition is when omega t is larger than pi but smaller than 2 pi plus alpha. In other words, in the second half of the cycle over here, ideally the output voltage would be equal to 0. This is essentially why these are called half-wave rectifiers, because they only rectify on part of the input signal, or rather half of the input sinusoid. During the second half of this input sinusoid, there is no rectification, and the output voltage and current would be 0. So the output voltage during the conducting part of rectification is the all too familiar 1 over 2 pi multiplied by the integral from alpha to pi of the input signal with respect to the switching frequency. In other words, that is the average voltage from alpha to pi. This would be equal to the average output current multiplied by the resistance C in the load here, and that simplifies to root 2 multiplied by the input voltage divided by 2 pi multiplied by 1 plus cos alpha. The output voltage is maximized when the cos function is maximized, and this happens when alpha is equal to 0, and when that is the case, then the maximum voltage output is equal to square root of 2 multiplied by V, which is the input voltage, divided by 2 pi. As before, there will be two conduction modes for this circuit. There will be a continuous conduction mode and a discontinuous conduction mode. The current behavior for the continuous and discontinuous conduction modes are similar for the rectifying circuit, which does not have a freewheel diode, but have to be modified to include the fact that a freewheeling diode is now present in the circuit. So the two main advantages of including this freewheeling diode is that the input power factor of the rectifier can be improved, as well as the waveform at the load, which gives better performance by making sure that there is less ripple in the output waveform. Shown here are single-phase, full-wave rectification circuits. The first example makes use of two thyristors and a transformer, and the second example makes use of 4 thyristors in a bridge configuration. So the current waveform in the load will become continuous when alpha is defined as the arctan of omega L over R, and this is equal to the angle phi. If alpha is larger than phi, then the operation of the circuit will be discontinuous. In other words, there will be a discontinuous current flow in the load. If alpha is equal to phi or less than phi, then the operation will be continuous. For the two cases where alpha is less than or equal to phi and the circuit is operating in the continuous mode, then the output signal will be a fully rectified sine wave. So what can be seen here in graph D or graph E is that the input sinusoid still goes negative, but the output voltage remains a fully rectified positive sine wave. When the angle alpha is less than phi, then the rectifier sine wave will have a DC offset associated with it as well. For purely inductive loads, the output current is basically a square wave, and the average RMS current for all the harmonics in the square wave is equal to the average current, with the first harmonic current given by 2 root 2 over pi multiplied by the average output current. As before, there is some critical inductance, where the inductance has to be larger than a particular value to prevent the output current from falling to 0. This inductance in general terms is given by this long expression here, which I'm not going to read out, but there is an angle theta, which is the critical angle, equal to arc sine of V0 divided by root 2V, which is equal to arc sine of 2 cos alpha over pi. If alpha is less than theta, then the critical inductance is given by this long expression, but if alpha is larger than theta, then this can be simplified into the expression over here, because alpha is simply substituted for theta in this trigonometric expression over here. Finally, this lecture is going to have a look at single-phase full-wave rectifiers which have an RL EMF load. In other words, there is an EMF source in the load which influences how the commutation happens. So this is the same full-wave rectifier as before, except the source has been drawn slightly separately from the bridge, and the load now contains an EMF source over here. Once again, there are three conduction modes. There is a discontinuous mode and two flavors of continuous mode. First, the current will approach a load current of 0, but it will only stay there for a short infinitesimal period of time before increasing again. And the second continuous mode is where the current will never actually reach 0. In the discontinuous mode, there will be some measurable period where there is no current from the supply to the load. If E were to represent a motor, then the motor speed control can be controlled by alternating the switching characteristics of the thyristor pairs T1 and T4 and T2 and T3. Essentially, the motor speed can be controlled by altering the firing rate of the thyristors. For the discontinuous case, what happens is that the back EMF causes the thyristors to be reverse biased, and thus no current can actually flow from the supply to the motor. The angle at which zero firing of the thyristors occurs is given by I hat equal to arc sine of the back EMF divided by the square root of 2 multiplied by the maximum input voltage. And this is valid by alpha hat between being less than pi or greater than pi over 2. So this sits over here on the graphic. The angle at which the thyristors will start to conduct is given by a similar expression, arc sine of E over root 2V, except now the range for alpha is slightly different, with alpha needing to be larger than 0 but less than pi over 2. In other words, this is this region over here where the input signal must first exceed the back EMF before any type of conduction can occur. If the delay angle alpha is between alpha max and alpha min, then the load current will always flow. As always, the output current characteristic can be solved for by evaluating the expression for the loop inside between the bridge and the load. The Kirchhoff voltage equation for this loop is the supply root 2V sin omega t, once again equal to the voltage across the inductor, the resistor, and the back EMF. Something important to note about full wave rectification is that because the sine wave is being fully rectified, there is effectively a doubling of frequency. This means that the load voltage frequency and the output ripple will be at twice the input frequency. So if it were a 60 Hz source, then the ripple and output voltage would be at 120 Hz. As before, this circuit can operate, or rather have both continuous and discontinuous modes with regards to the load current. In the discontinuous mode, there is some extinction angle beta, which needs to be solved for in terms of alpha. For this type of circuit, the approach for solving beta is the same iterative approach used in previous circuits because beta is strongly dependent on the value of alpha. Additionally, the extinction angle is dependent on the back EMF as well as the impedance seen in the lobe, which is a combination of the resistive and inductive components as well as the switching frequency. Once again, there is also a continuous mode of operation which starts operating at this boundary condition here, where the current only approaches 0 but never quite reaches it before increasing again. There is also a critical inductance value which is required to prevent the current from approaching 0. Conceptually, the continuous operation and the critical low inductance are no different from simpler circuits such as the single-phase half-wave rectifier, but the math which describes the output current waveforms are now slightly more complicated because of the full-wave rectification. The approach for deriving these equations for the output current during continuous and discontinuous operation is no different than for more simpler circuits, and is encouraged for the student to read the textbook to have a look at how the author has derived these expressions for a full-wave rectifier. And this concludes this lecture.